They can do 115 billion protons per bunch. The beam size is 30 centimeters, and you can get the idea about what this was created. And if you now look at what happened with history, is that the whole idea about the theory came out in 1964. Higgs was one of them. Engelhardt was also involved, and it's called the Higgs boson particle, right? So idea came in 1964, and in 2013, Higgs and Engelhardt got the Nobel Prize for the work. So it was a 48-year search. The theory was in 64, Large Hadron Collider and the concept experiment was done in 1984. Construction started in 2001. Operation is finished in 2009, and discovery happened 3 years later because they had to collect actually a lot of data. So you can see that to be able to make new discoveries in science, a lot of effort goes into it, a lot of engineering goes to it, a lot of new instrumentation needs to be developed to be able to, and a lot of innovation needs to go into it to create what you want to actually discover. So the question is, what else can you do with the Large Hadron Collider? So I asked my friend Harvey Newman, said, Harvey, what do you think? Harvey is a professor at Caltech for a long time, and I got to know him about only 2 years back, because he showed up on a conference on computer networking, which is a meeting on computer networking, where I was there. And I said, why is this physicist actually attending this meeting? So that's the first time I met Harvey, and then I had met him many times, had conversation with him. So he kind of wrote it in a very simple way at 3 things. I'm going to put everything in one slide. This very busy slide is hard to read it, but I'm going to highlight 3 things. So we wanted to know more beyond Higgs boson. We wanted to more fundamental theory of nature, first thing. So second thing is the Standard Model has no place for dark matter particles. So we also do not know what dark energy looks like. So those revisit petabytes for a second. So we start with a 1 byte. The 1000 bytes is a 1 kilobyte. 1000 kilobyte makes it to 1 megabyte. So most of your phone can. So most computer disk nowadays you can get a 100 gig hard drive up to 4 terabyte of hard drive there. So petabyte is 1,000 terabytes data. So if I now go back to the byte, it is 10 to the power 15. What makes it a petabyte? So you can now see that easily that you cannot actually store in one disk. You have to have multiple disks to be able to do it, and everything to kind of, and then somehow you put it together. And that's where the idea of a network comes in, which I'll visit in a little bit. So here's a very interesting quote from Dan Marone of University of Arizona. He says that, it's equivalent to 5 petabytes is equivalent to 5,000 years of MP3 files, your music file, or it is like entire selfie collection over a lifetime of 40,000 people. That just give you a context of amount of data that is collected to be able to do it. So what you suddenly realize, to be able to do science, data plays an important, very, very important role. And not only that, it's a lot of data we're talking about. So here is the numbers for that. I got it from Frank for Large Hadron Collider. If you can look at it, it generates 1 to 10 petabytes of raw data per year written to a tape, not counting simulation and everything. There are 2,000 scientists working on it, 1,200 PhDs, 180 institutions, 40 countries. They are being able to access different sets of different types of data, different level of granularity of data. So you can see there what it is. So how do you make this happen to be able to make something available? The Frank also gave me another very interesting quote. He said that what LIC can be thought of as a 100 megapixel camera take the picture every 25 nanoseconds. It's like just clicking it like this. I really like this analogy of what he said about how much data actually you are collecting and whatnot you are trying to do it. So I thought I'll quote that for you guys. So this is where it's a good point to kind of take a step back and say that how do we actually computer science, how do statistics, computer networking fit into the picture? Already I've been talking about the amount of the data. So data amount basically said it's lots of data. Secondly, you already found out that I'm kind of hinting a little bit about the error in measurement, sparsity of data when you are trying to take a picture of the black hole image. Statistical techniques and statistical confidence become very important. And the other most important thing is that how to move the data around, how to reach where the data is also important, because not everybody can go everywhere, right? So that means you need to develop new computer vision algorithm with noisy and sparse data, and they actually plays a role there. So in the case of the black hole image, there are multiple different sources of error. So I'm going to give you a very high level picture. Atmospheric error carries the phase. If you know the phase and amplitude of a signal, sinusoidal or cosine signal that some of you learn in physics. So the phase is unknown, first thing, because of where the telescope are located. There's an amplitude attenuation that can happen, additional amplitude errors they find, and so a bunch of different type of error can happen. So error actually creeps into the measurement as you're trying to measure it. So that means that when they try to do it, they actually realize that there is no single way they can actually do the black hole image. So two separate teams of researchers try to innovate, develop new techniques to be able to do the image. So here's a very quick view of what it is. This is a thing I showed you earlier. You can see the black hole image on the left. Telescope, there is I got measure. Then you have to do what is called basically you have to invert it. What does the reconstruction means? I have to get back to what it is. In the context of mathematics, what is it that? It's taking an inverse function. But inverse function is not like a closed form function. It's not like saying f of x equal to x squared. That means the inverse is going to be what, right? That you can calculate it very easily from your basic algebra, what the inverse of a function, because you have y equal to 1 over x squared, then it's x equal to, 1 over square root of y. You can actually get that back, right? But here, you don't have a function that actually you can. That's where the algorithms plays into the mapper. Then you can do. People who are familiar with fast Fourier transform, techniques like that can be used here. On the right is the other one. That's the one you can see the similar thing is there. There's a little bit more information there. Basically, what you find out is showing it that where the noise is appearing. the thermal noise, systemic noise errors, phase errors, amplitude errors, all of this time appearing. So only thing you can do is from something called statistics, called the maximum likelihood principle, you are going to be able to use that to be able to reconstruct that particular picture, right? So two different, eventually what I think Katie was the one on the right, the maximum likelihood principle, and they give different. So this is, that's also why sometimes it is very important to independently two different ways to do it, so that you can compare and you come to the same conclusion. That's very important in science. So eventually the 4-step process of making a picture of a black hole is that you actually have to first try to test synthetic data. That means you take an image, you randomly change the image a little bit to say that that's not good enough. You have to do it on a bunch of different pictures so they have confidence there's a robustness with the result. But you have one clue, that the clue is that you know what a black hole is. You can imagine a black hole is going to be. Black hole is not going to look like me as a human being. So you can immediately rule out some of the images that is not going to be even part of this thing. A human being is not going to be part of a black hole image, right? So you can actually narrow it down through filtering algorithms to see what images to compare it against. That's where machine learning techniques and everything comes into the picture. So then I said that, okay, all of this thing to connect it, did I say that I use a network to connect it together, right? So the answer is yes. So I again went back to ask Frank, my friend Frank and Harvey to answer my question. I asked Frank that when did you realize you need a computer network for the work in physics? Frank is a physicist, by the way, right? That you need to do. He said it's 20 years back in 2001. When he was working at Fermilab, he realized that I got all these processors I need to connect. He wanted to compute something and do something, and that I got to connect it together. No one computer can actually make it be able to do it and whatnot. I'm not going to read all the details of this thing. And then he talked about that we spend a lot of coming here for Commission of Network and Endpoints in worldwide because they want to give access to scientists all over the world who want to do it. So the network is about the only way you can do it. The Harvey gave even a more interesting answer. So Harvey said that he realized even back in 1981. By the way, Harvey is probably about 70 years old. He is so energetic. I have never seen somebody like that. He's so excited about what it is doing. I hope I'm excited like him about science and what's up. He said that in 1981, he moved from CERN in Switzerland lab to Hamburg in Germany. And then he became a faculty job in Caltech and he was going to move back to US. And he suddenly realized that how is he going to be able to actually the work data with the experiment that was overseas, how can we connect it? So he actually, which I did not know, he was an early reader in high energy particle physics to connect the international network going back to 1981 and 82. He's a trailblazer. That's what you call somebody like Harvey. And Harvey is the nicest guy you'll ever meet. He'll talk to you. If you send him an email, you meet him on the street, he'll talk to you. You know, he has so much energy and whatnot, you know. And he cares so much about what he's doing. He's now looking at the next set of network issue. I'll talk about that later. So he made a lot of interesting thing about it. So here's a picture Harvey shared with me about that. If globally somebody wanted to data flow, you got the CERN. I don't need to go all of the details. CERN in Switzerland is there, Chicago, Bologna, Paris, London. They call it the different tier 0, tier 1, tier 2, tier 3. So you got different centers connected, different institute connected like that, all the way back to some filter data you can actually, because you don't have to move all the data, you can start the compute and do from your workstation also. That's the beauty of a computer network. You don't need to download all of these petabytes of data I talked about, right? So this is actually a design, you know, done it in Caltech, that this is how it needs to be done to be able to access all the data that you want to talk about. Okay, so I'm going at a pretty good speed and should be done in about a few minutes, all right? So just bear with me, then I'll be happy to do Q&A. So here's the picture Frank shared with me, that global big data science, that that how different places are doing storage and compute cluster around the world. There's a picture that you can see obviously in the North America, South America, Chile, you can see it there, different places. Europe, there's a lot more nodes in there. Africa, South Africa, you can see it. You can see nodes in India. You can see it in China. You can see it in Japan, Australia. Everything is connected by a network that the scientists can actually access it. And so what is important to realize that it is making it much, much easier to access it. So to give you an idea, I put the link in there. You can go to opendata.cern.ch. Anybody can go in there, can set up an account, search for the data, can do it from your laptop anywhere in the world. Because the whole one other goal of what they are trying to do is that trying to make the data available to scientists who can actually be able to access it from anywhere. Because it goes with a very important fundamental premise that if you can democratize the way you make access available to everybody, then you would be surprised who can come up with a new solution in the remotest part of the world, because they have a different way of thinking and came up with an idea to do something. And we see that happen all the time. And that's why, to me being an expert in computer networking, my goal is to be able to see how can I make, especially for scientific data, accessible to as many people, as many researchers, as many students, teachers as possible around the world. What can we make it? How can we make it happen? This is also where your government policy becomes very important. Your government has to feel like that this is important to do, so that, and when the moon with the India sent us to moon, that people got so excited about being able to send to rocket there. And so, it is actually can be very, very exciting. And don't think that is only limited to science, because science eventually becomes engineering and eventually becomes product. Think about something like fiber optic. Fiber optic is today connects the internet all over the world through the submarine cable and whatnot. Fiber optics was a idea in physics for 40, 50 years back, right? So it takes that long to be able to, that's why physics is important to do it now, so that we give something to be able to productize over the next 30, 40, 50 years. That's why you think about why these problems are important to look at. I want to quickly switch gear for 1 second to give you a couple of, I've been talking about physics, but I want to give you a couple of quick pictures. This is a digital pathology. I was talking to one of my colleagues, Praveen Rao. So what it is that they're going to make digital pathology, the FDA is the Food and Drug Administration in the United States. They had actually allowed marketing of what is called whole slide imaging. The interesting thing here is that, again, going back to image I talked about, each image in a WSI is actually 5 to 6 gigabytes, one image. And there are Sloan Kettering Cancer Center in New York City. They alone itself has 1 million of these images. Now imagine being able to make that accessible for medical diagnosis. How can you make that easily accessible, knowing that the image in the first place is already in gigabytes, and your network are now the constraint to be able to get it to a doctor who need to see something and a specialist who need to see. So it is the implication for telemedicine and what we want to do also with that. Here are a few other examples, couple of telescope example, polar geospatial data, very exciting stuff. It's amazing. You want to go to this link and look at some of this picture. It's like you are awestruck. I have friends in biomaterials. They have been working at my University of Missouri, Kansas City. They're working in biomaterials. Basically, when you have lose a tooth, they put a crown in there. The crowns have a different problem over time with aging. Biomaterial basically says that if we can make the material in a way, it can essentially grow with the person over time. So it needs a lot of this thing. But to do the research on biomaterials in the School of Dentistry, so they use what is called a confocal and multiphoton microscope. And what I found out, each of the image they generate is actually 10 gigabytes. So if they want to even share that data, they have it on their lab to outside to other researchers, they are actually stuck right now. One more example, everybody talks about DNA nowadays. Actually, if you look at the entire DNA with the 4 DNA base pair, if you can code it and multiply the numbers, you find out that one person's whole genome sequence will take 1.5 gigabytes, just one person. And you know how many people are in this world, right? What is it? Last count, 7 or 8 billion people we're talking about, right? So if I'm not saying it is you are going to be able to do or collect everybody's, but even if you do a small number of them to want to give access to be able to compute something about, let's say the COVID thing we're talking about situation, then you realize that you have to do a lot of data processing and whatnot. Networks are becoming very, very important for that. So basically what this is saying is that we're entering the world of what is called a data-intensive science. Those are the examples from different fields I talked about. I'm going to spend next 4 or 5 minutes to wrap up about what's the computer network and what's the new exciting thing in computer networks we are thinking about that can help you to do better. So first thing about the role of a computer net is very important, which is that you, as I said in the byline, move data faster. That's the basic goal, right? So if you want to move data faster, actually you find out that it's not easy as it seems, because it is governed by a very simple principle. In computer networking, we call it bandwidth delay product. And bandwidth delay product has another name. We call it a window. Window may sound like a very funny term for many of you. It's not, of course, the window in a building or anything. Window is basically means the size, how big I can make it in terms of a byte. And so in the specific protocol, we call it TCP protocol. It's called a TCP window sometimes. Good. So if I actually look at it, I can actually look at say that if I want to have maximum window size, think about like the aperture thing I talked about earlier, right? So if I want to have a maximum window size, it's going to be a multiplication of the bandwidth and the delay. So if you invert this formula, then you find out the bandwidth basically means the data rate is going to be limited by the maximum window size and divided by the round trip time. How much it takes. You must say, how much does it take for me to be able to go from here to let's say, in terms of not me, the data to go to India and come back here, that's called a round trip time. Okay, so that round trip time, as a human being, you and I actually don't perceive is a whole lot, but it can be in the order of almost a second, from 250 milliseconds in the US, within the continental US to 1 second, or even a little bit more than a second. Of course, there are other glitches and stuff like that. So what I want to tell you, without going into all the details about how TCP, the protocol, works, basically what you want to keep in mind is that at this point, we cannot get to the full window. We can only go up to, rate-wise, we can only go up to 75% of the maximum bandwidth or the data rate because of the way everything works. So although I'm going to give you the theoretical number in the next slides, but you are going to see that how that is going to matter. So first, before I can do that, I want to think about, for those who are not familiar with computer network, if you have a large file, what we do is break it into small chunks called packet or segment. So each packet or segment is sent independently in the network. And let me see if I can make this animation work. So here I have routers or nodes in a network on the computer network, and your grandma is trying to send an email sitting on her this thing. So what happened is that the message is broken into 3 pieces here I'm showing you, and it's going to go through the network. It can actually go through different ways through the network, all right? It doesn't necessarily have to go between same things. Think about almost like your road network. Let's say your brother is driving a car, your sister is driving another car. Each of you are going to visit your mother. You might be driving different way to get there until you get there. So think about like that. So when you get there at the end, it has to do what is called a reassembly. Okay, and so that if it arrives in different order, like your mother knowing that who is the oldest, the next youngest, and the next youngest, same way you have to and that's what your computer is doing it. So when I talk about the window in the previous slide, the window means window is the size of the number of bytes on a particular flow of connection, I can put it on my laptop, for example, when you're downloading a web page and whatnot. So here's the things. So there are a lot of numbers here. I'm going to make it simple and easy. So I don't want you to read everything. So if I set up the window to be 0.066 megabytes, which is actually 65 kilobytes, and 65 kilobyte is the TCP window size. So most laptops, to just give a point of reference, is that's how much a laptop typically sets it up. When I started working with computers 25, 30 years back, the window size was very small on a computer. It was like 1,000 bytes when I first started. So that's now, so if you have a 65 bytes, and if you say latency is 100 millisecond, you can actually, maximum data rate you can get is actually only 0.05 gigabit per second. So if you have a 100 gigabit link, your link is going to remain empty. Your bottleneck is actually the window size on the computer. So that means that if I can increase the window size, that's what I did it on this column, and make it very big, 655 megabytes, almost a gigabyte of window. By the way, your laptop cannot do it right now. I'm just putting a number to show you what happens. Even with that 100 millisecond of delay, I can only feed up 52 gigabit per second. So if I have a link of 100 gigabit per second, I cannot actually fill it up. It's not going to be. So we have a limiting point there to be able to figure it out, which means that we need to build new computers, new memories that can increase the TCP window size bigger, and also look at memory management in a computer, how best we can actually do it for that purpose of it. So anyway, I'm going to skip a couple of numbers here. You got the point about it. But what happens is that now let's put a file size. Let's say I have a 1 gigabyte of file I want to transfer. If you have a very small TCP window of 65 kilobytes with 100 millisecond of latency, it's going to take you 25 minutes to download it. Okay, unless you can increase the window size, a fancy computer, you can actually reduce it to about 3 minutes, unless you can go to 655 megabits. These are only simple numbers. Just I did multiplication division, nothing fancy, to be able to understand what is going on with this part, right? And then I said that if I put the file size, I kind of put it there. Let me skip this one. For a petabyte of file, if I have a 65 megabyte of window, I can actually 100 gigabit link, I can only fill it up 52 gigabit per second. It is going to take me 2,543 minutes if it is just one file. Luckily, you don't have one file when they collect in LHC and whatnot. These are small files, a different size that you can parallelly send it. That's the helpful, and that works better with Windows. But we're getting to the point that this is a serious problem we need to start thinking about from a network protocol point of view. And the one new factor that is appearing is what is called a checksum error. That means when you transfer a file on a network, like say download a file, the reason you don't see an error is what is called, it does a CRC check. CRC check or checksum is basically says that anytime you send it something on a wire, if you know your basic electricity, that is going to have some noise. If somebody taps it, the power goes up a little bit, and what it is, all those analog signals eventually get translated to digital value. That means, what it means is the 0 can become 1, and 1 can become 0 because the amplitude change or phase changes in the signal there, right? So that means what happens that every time I send this packet I talked about, every node in the network, the router, has to recheck and say, is this still a good data? Only then I'm going to forward it to the next guy. So luckily, the technique that was developed 25, 30 years back, it is 10 to the power negative 16, I think, is the error is very small. So if you download a megabyte of file or so, you're not going to notice anything. 300 meg, 200 meg, the likelihood of that happening is very, very rare. So, but what happened is that, let's say my packet size or segment is 1 kilobyte and I want to do a terabyte. What we found out is as you get to the 1 gigabyte, so 1 petabyte of file sizes, your likelihood of having those kind of error that is going to be unnoticed by the network or any of the routers in the network can be between as small as 100 to 62,000 packets. Now, that's a big number. So if my network is not able to give you the data, so that means I have to correct it in the protocol. Secondly, if the science is depending on me delivering the accurate data, then they expect me to do it. So I cannot live with the error that I am likely to get. I have to do new protocol, new ways to think about it. So that's the exciting part about computer network. So usually what we say that maybe you could have compressed it. Why don't you compress it and send it? You know what is funny? That if you have a 1 gigabyte of data and try to compress it, it's going to take you more time to compress it than to actually send the file. So you basically, and think about now 1 terabyte, it's going to take you more time to compress it. So you have to take into account that factor. So you are now doing a trade-off between compressing before transfer or not doing it. So the TCP protocol right now works end-to-end like this, from one end to another, just transfer it and get it there. A new idea we're looking at is called in-network storage and compute it. Then what you do is you do in a chunks and bigger chunks and transfer it, kind of store it for a short amount of time, check the data integrity of all the information, and then forward it and all the stuff that can happen, right? So for that, we are actually just, in fact, this is one of the projects I supervise at the NSF. It's a $20 million project called Fabric. It's the next generation network testbed. And this testbed is going to connect to, also eventually going to connect to CERN in Switzerland, and also going to connect to the telescope in Chile, down in South America. And so, but we are using this testbed to try out new, innovative networking ideas, pushing the boundary so that it can help to do better science tomorrow. So that's what we are trying to be able to do it. So let me kind of finish it with just some 1 minute up, a couple of minutes up. That I always said that these things are very important. Basic physics is you want to understand it. Basic statistics, measurement error, statistical confidence interval. With computer programming and algorithms are a good thing to know. Basic chemistry, basic biology. And I don't want you to forget the economics is very important. You want to understand that how economics plays a role on what you can afford to build. It's very important to take into account in terms of what you are trying to do actually. What can you do? So for example, right now, Event Horizon Telescope has 6. They can only get an approximate image of the M87 black hole image. The next phase that NSF just funded it is the design of the next gen Event Horizon Telescope is going to actually put more telescope to be able to do a more accurate way to be able to collect it. But the economics at plays a role is that what can you afford to do it, even for $1 billion worldwide effort to be able to do it, right? So you want to understand that thing. I always say you want to focus on the fundamental, understand the basic things and whatnot, and then try to actually see what you can actually do, learn from the basic ideas. Newton's law of physics, very important thing. Basic idea. I talk about the driving principle in computer network, that file transfer with bandwidth delay products. Understand what it is and what it means, right? Analytical thinking. You want to think about what it is. Just think about it, what it is going to happen. What if I change something? How is this going to, make maybe different in what we can actually do it? And you want to use number to get insight. That's why I showed you the numbers in my tables earlier with the transferring a file. I know I went a little faster. I'm happy to go back based on a question and answer. And so you can then say that, okay, we want to use number to get insight. Is my numbers coming out correctly? Think about it. Is it making sense? And this is where one other thing I want to say is that when you think about and do something, it's very important to also focus on writing. Jot down your ideas. It could be whatever it is. Writing helps you to think it straight. Write it in your own words. It doesn't have to be perfect. You just want to write the ideas, put it together, whatever it is. Writing makes you actually think better. For me as a person, I have gotten so much better because of writing over lifetime. I was a terrible writer to start with in high school. You don't want to know my marks in English and Assamese back in class 10 and class 12. And so, but I think it was something that you can take it as a lifelong goal to try to make yourself better. And so in summary, I really want to say that science is very exciting, new things to explore, data-intensive science I talked about, interdisciplinary nature of things, basic understanding is very important. Simple numbers can give you insight. I always say that common sense, imagination, and curiosity are very, very important. And that you want to always keep in mind. And I think you want to look at everything as a fun. You want to do it because you actually enjoy it. And so I'll finish with a couple of quotes. Einstein said that logic will take you from A to B, but imagination will take you everywhere. And the Tolkien's quote is a very favorite one of mine. It says that not all those who wander are lost. Thank you very much.
Thank you, Dr. Mehdi,
for
your nice presentation. So actually, I have checked the chat box. We don't have any question. But now may I request the participants to put forward your questions, any queries that you may have. We are now beginning the Q&A session, question answering session. So anyone, please feel free to ask, put your question directly to our resource person. Anyone, please unmute your mic and you can directly ask the question. Manoj Dekha, Manoj, we have few student join korisile niki oloman?
Yes.
Okay, students, you can put forward your question. Feel free to ask the question because
yes, Assam is Assamia thudilo hobo kono kotha nai, it's fine. Yeah. It's okay.
Sir.
Okay, I'm starting to see some comments here if I read it. So let me see if I can open the chat here. Give me 1 second. The chats are disappearing. I'm going to stop. Maybe I have to stop. Okay, here it is. Give me a second.
I think there's a question about.
Just a second. There's a question about Hawking's radiation. Is it possible that the size of a black hole can be decreased? This is a very, very interesting question, important question. But can you hear me still?
Yeah, we are able to hear you.
Okay, great. So this is the question was that this person that I have read somewhere about Hawking radiation. Is it possible that the size of the black hole can be decreased? That's a good question. With my knowledge of physics, I do not know the answer to that. Maybe your physics teacher will know that question. So that they can answer it. But I suspect is that it may the black hole is my understanding of black hole, right? It is actually evolving. It's not something constant. Even for M87, it may be actually growing or going differently. So I do not know what a decrease of a black hole really means. Maybe it loses power and whatnot. So somebody who studies that more probably able to talk about it. So here is another question. Somebody said, what programming language for data science? Programming language, obviously, nowadays Python is very important. Python's pandas. R is another important language for data science. Python is very popular with scientists also. If you're a scientist, many of the scientists still use Fortran, but they have written nowadays interfaces that they can talk with Python or other languages. Another thing to keep in mind is that even if you're a physics student or chemistry student, you may not need to write everything from scratch as a programming. Learn some basic programming, because many of these sites that I mentioned about, they actually have the software code for analyzing molecule and stuff already there. So if you learn the basic language of using it, what it is, you can actually go and take a look at the code. You can run it yourself. So that's very, very important to kind of think about.
But only if it's open source, right?
Yeah,
Because,
the scientific data, most of the thing in scientific world, it is open source actually. So you can.
But if you work for a company or something,
No,
you'll be a
company. I'm not going to
proprietor.
talk about company. That's not this talk is about. So
Or even
I'm just
government, it has to be
so
proprietary.
scientific work, many places you can actually access it, right? So another question is about statistical inference and techniques. Can you please tell me, sir, one used or can be used? Aha, very interesting, right? Let me kind of talk about this. Inference idea can be derived from the perspective of parametric statistics and whatnot. So you can actually look at information from statistics to I talk about maximum likelihood principle that earlier I talked about. Actually, my sisters both are statisticians. They probably know more statistics than I do.
Yeah, maximum likelihood.
Yeah, maximum likelihood principle. Basic stuff in statistics, very, very useful. You realize that that's what they use for being able to reconstruct the image for the black hole, right? So you want to actually think about those sort of information. One question was, sir, can R software and Python be used for inferences? Yes, many of the Python, especially Python Pandas platform and Jupyter Lab and R software, they actually, people have contributed codes to it. So you don't have to write everything from scratch. They already have the technique for let me talk briefly about linear regression, very important technique in statistics, linear regression or nonlinear regression. Those packages are already available there in Python Pandas and R software, RStudio software. You don't have to write it from scratch. It is important that you understand what linear regression means. That's what I mean, fundamental knowledge. You understand what it is there. So if you're not quite familiar with linear regression, that you collect some data points that you want to see if a line is going to, straight line is going to fit there, right? So you can see that it is a mathematical way to do it, that calculation. And so, but the packages are not there that allows you to be able to do that information. Let me first finish reading the questions as I can see, then interactive way I can answer a few more questions. Let me see if this is sometimes going too fast. Our inference, I talked about the
dark energy.
Dark energy released, released by, so who is a physicist here? So who is going to be able to answer that question? Any physicists want to answer that question for me from Duliajan College?
Poppy, are you there? Poppy?
Poppy, are you there?
Maybe she's not there. That's okay.
Anyone from the participants even can.
Yes, anyone from the participant, you can talk about it. Yeah. Yep, dark energy, obviously they're related in terms of what it is. The second question is very good. How do we use computer simulation in science? It's a very, very important question, because what happened is that simulation comes because first you can think about simulation come in terms of a time, because you're going to increase the time in discrete time steps. You're looking at, let's say, every second of information. And if you're looking at, for example, a rotation of the Earth, right? You wanted to understand what is going to happen, let's say, 1 million years from now. You know the gravitational force between the sun and the Earth. So you can take that into account and look at the value, and then you can look at the time-based step simulation. So you actually write the code and say that this is what it is going to be doing, and you look at the time as a discrete measure of time. You can do it every second, depending on what you're doing, or you can do every minute, depending on the granularity of information you want to look at, so that you actually can simulate that information. I believe some knowledge of computer simulation in science is very important to start introducing even at the college level, because there are packages already there. So you don't have to learn everything from, it's like using your Excel as a package, software tool, right? It's like that nowadays for many of those. So you can actually use that in your class to simulate it and whatnot for your class. So let me see. Very fundamental question, sir. Why is universe so mysterious? Why don't know much about dark matter and dark energy? Okay, so universe is mysterious is that I always look up in the sky, on a clear day and wonder what's out there. The mystery of the universe is probably one of the biggest mysteries that we do not know. I don't know if I do not think in my lifetime we'll get an answer to that question. But all of this, what we are doing, hopefully it helps us to understand the mystery of the universe, about all the things related to how particles are created and whatnot. All of these things are, we are going to understand better, as time moves on. So going back to Newton's quote, standing on the shoulder of the giants, basically, you can only make the step, you can make it right now. So the next generation of scientists can do the next step to take it to the next one. The question is, what do we don't know about dark matter and dark? Because it doesn't show up easily here. It is out there. So that's why you need a special instrumentation like the Large Hadron Collider, so that you can actually collect certain information. There is also, by the way, ice cube neutrinos thing that is in South Pole, I think. I didn't have time to talk about it. So you, because of the rarity of that, maybe you will get the signal coming from the, from another place, because in light years it is moving, you catch it, right? So that's the hope with those kind of instrumentation right now. I gave you an idea about the Higgs boson. 1964 is one theoretically they talked about. If you go back to Einstein or Bose, actually, so it turned out Bose, who first did the Bose-Einstein statistics going back, 100, a little bit over 100 years ago. We have come a long way in 100 years from imagining that the light takes a curve around the black hole to be able to actually get to drawing an image today. So I'm so hopeful about next 100 years, that what it is going to take us to be able to figure out. And hopefully that takes us one step closer to understanding better about the mysteries of the universe. How many black holes till date detected by Event Horizon? Event Horizon, I think, tried to take picture about only 2 black holes, but the M87 one was the better one because of the distance and the position and whatnot. That's what I understand. So they did another one. I forgot that one. The images were much, much harder to be able to do it. This is another reason why the next generation of Event Horizon telescope, when they are going to put a new telescope, many more telescope and different apertures and stuff, is the hope is that we'll be able to take a better picture and more black hole that you can actually take. Okay, so the question is, how did we take picture of the black hole if the black hole traps light and cannot actually be seen? Remember, we're not taking a picture of the black hole. We're only taking a picture of the light around the black hole. So black hole is there in the middle. That's what you can see, the fuzzy part of it. Light is going around it. So you're only taking a picture of the light around it to say, hey, the black hole is sitting right in the middle of it. That's basically all we can be able to say about it. How can we get free data sources? Somewhere in the slide I mentioned is that open data, if you search open data or CER and CERN in Switzerland, actually they get a link to that one. I do not know all the detail, but they will have some information on how you can access data and whatnot, right? Sir, commands are available for both R and Pythons. Yes, there are command or packages available on the command line that you can do for using with for many of the packages. And by the way, there are probably many videos on even on YouTube to learn how to use those packages. So you can use YouTube as a resource. Coursera is another site where they have it. So you can use many online resources to actually see how then you can use it. Secondly, there are a lot of not mailing lists, a website who actually help you, help answer your questions for you. And they do not say that, oh, you don't know anything. They will just answer your question. They'll say, oh, this package is available here. Please go use this package. So many people are helpful around the world. So how can we predict dark matter? That's beyond my knowledge of physics right now. So I cannot answer that question. I have to rely on my friends who know more about it. Are all statistical tools available in Python? Pretty much all of them, but if you are needed more sophisticated tools like what they use it for black hole imaging, they probably have to write it differently because of the amount of data. Because right now, what you get in Python is, you can still do pretty much megabyte range of data fairly well. But if you wanted to run that on a bigger platform, you may have to use a cloud computing platform and stuff like that. Then may have to do some distributed way. So there's some challenges there as the amount of data gets bigger. But you can always start with small amount of data to understand, to see what you want to look at. And somebody said to request share the presentation. By the way, my presentation file is, I think, about 150 megabytes, just for your information, because I had the animations and everything. So that actually is 150. So it is not an easy way to exchange or to make it available, but I will try to see what I can do about it. Dark matter, Poppy Hazarika asked a good question. Dark matter and dark energy are...
CC wrote the answer, actually.
Okay, so let me read the answer for everybody. Dark matter and dark energy are predicted due to inconsistencies between result and prediction. There are many experiments like rotation curve of galaxies, gravitational lensing that predicts or say that there is something else. So thank you for answering that question. So I do need the help of a physicist. That's why I said I rely on the soldiers of other people to be able to make the next step and whatnot, right? Somebody said, sir, my Twitter handle. I don't use Twitter a lot, but I do have it. I'm happy to share that with you. My Twitter handle is, I'm going to Netrel, because otherwise that's my Twitter handle. I just found it. So what is the role of India in terms of research in the field of computer type and cosmology? Are we doing enough, and how the future generation of India could help in this? This is what I call is a $1 million question, right? So what I mean by that is that India has made tremendous progress in terms of science and engineering in the last 50 years. And this is very heartening for me as a researcher and people I do that I know, people I work with. One of my good friend, Assamese friend, is actually involved with the Deepak Das. He was involved with the whole, the Chandra that was sent to moon. So he and I talk about once in a while when we get an opportunity. Again, I think part of this thing is that I believe the government also plays a role. What I mean by that government has to think that the science policy is a very important thing to think about, and accordingly allocate proper amount of funding to be able to explore it. As I talked about it, that when we are going to data intensive science, be it physics, be it chemistry, be it biology, DNA, anything you can talk about, that the amount of data, or even for general information, there's so much of data that need to be handled. And so you need to have a strategy about how you want to make more research possible for the scientists in India. So I think hopefully more of that will happen, but I can see a big progress already in that area. I do not follow the science policy in India in detail, so I cannot give you a more specific result in terms of what you may have. Those are the questions I saw so far. Okay, so here's another question. We have an overflow of data, all the fields across the globe. The management and processing of data in a proper way is a big question. What is your view? It is a big question. That is my view. So that gives you new opportunities to think about new problems, right? So think about basically fishing, you know, borokhui bua, right? You know, I used to, I used to go do borokhui bua. I get one fish or two fish. Let's say I catch 2,000 fish on one day. My whole small aquarium is not going to be able to hold it, right? It's not big enough to be able to do it. Secondly, maybe I want to market it. Then I have to worry about keeping those alive until I sell it. So you have to start thinking about the new set of problems, right? That's why this is so exciting, because one problem in one domain of science triggers that, hey, I need to develop a new technique. So, for example, new statistical techniques are being developed because bigger data needs bigger, different ways to look at it than what you need for a small amount of data. So I can say that between you and me, I can draw a line very easily. I'm just there, one line, I can draw it. But if there are 1 million data points, I need to say, connect this to this 1 million data point. It's not easy to do it, right? So you have to then come with new ideas, new algorithm, new techniques. And this is where the cross-disciplinary, interdisciplinary way to look at things are very, very useful. Let's see. Very interesting question. I have heard that the whole universe is a stimulation. We live in a stimulation. Well, maybe we do, you know, so we all live and die. So if you look at it that way, you know, maybe we're part of a bigger picture that I don't know the answer to, right? So we may be what it is there, you know, we don't know. Maybe someday we'll find out. Will it happen in my lifetime? Probably, I doubt it. But if we continue to explore the scientific things, that actually allows you to go learn more. I want to say that many people think that science is isolated. The answer is actually not true. What I mean by want to say is that science actually connects it that you realize that you actually need to build new and better instrument, because you want to collect different type of information and stuff like that. So science itself can be think about as a business in itself. So if you are going to design a new telescope, you have only the idea a scientist needs it. How do you actually design the telescope? What do you want to do in terms of being measured? Can you do that measurement? There are a lot of interesting, innovative engineering questions and problems that comes up. We all face challenges with that. Economics plays a role because eventually money is not infinite. You have only a finite amount of money to make a decision about engineering design problem. That given a particular thing, how much actually, what I can actually be able to do within that time frame. Okay, so my sister is asking me a question. Can you give a simple example of error in other fields and tell us how it can be handled? Okay. So the simple example I can think about is that is the election polls. You know, you guys know about election polls, right? Before an election comes, there is every small company or some entity is taking poll. So if you have more than a billion people in a country like India, there's no way you can ask everybody who they are going to vote. Secondly, even if you ask them, they're not going to tell you the truth. So that means what happens, we have two forms of error here. The truthness of the information is one form of error. Second thing is that because we cannot ask 1 million people, we have to only sample it. Maybe 1,000, 10,000 people who are going to sample it by either through internet or by telephone call and whatnot. So we only have, let's say, 10,000 data points, and I'm trying to predict what the country is thinking about something, whether science is important or not. So you know that my error is already built in because I only have a sample, right? So I only have a sample. So for that sample, that means what I have to do, only thing I can do is that I can look at the confidence interval. So if you look at an election said that one party is going to get 50% of the vote, other party is going to get 45% of the vote. But if you read between the lines, somewhere hidden, they will say, oh, there is a 5% margin of error. That means 50% means 50 plus 5, 50 minus 5. Because based on the number of data points we collected, we cannot give any better measurements than better confidence than that information. Make sense? So this basic principle applies it to any areas of science because you always have some error. If we have some error, how do we handle error? You have to have the confidence in the data. Then you look at the confidence interval using statistical techniques so that you can actually address that.
Okay, thank you, Dr. Mehdi,
Okay.
my elder brother. Yeah.
Thank you.
Okay.
All right.
So, do you have any more questions? I don't think so. So actually, the time is a constraint. We know that. Very happy to have you. Actually, thank you very much, Dr. Mehdi. And we are really
You're very
excited.
welcome. It's my pleasure.
Yeah. So we are coming to an end actually. So now I request.
Hello.
Hello.
Hello,
Principal sir.
Can I make a comment?
Yeah. In your inaugural speech, we have had.
Can I make a comment actually?
Sure,
Yes,
sir.
sir. Yes,
Sure,
sir.
Yeah.
Yes.
Yeah.
Thank you, Professor Mehdi sir. I apologize as I could not connect or I could not communicate you all due to some technical hiccups in the beginning part. And I use a quote to express my gratitude to you, sir. Actually, the quote is, life laughs at you when you are unhappy, and life smiles at you when you are happy, but life salutes you when you make others happy.
I see.
So
Okay.
we really salute you, sir, as you have made us so happy by delivering your talk on this fascinating field of interdisciplinary science. Am I
It's my pleasure. Thank you very much. Okay. My pleasure.
You are.
Okay.
So
Thank
we
you,
are
sir.
coming.
Thank you. Thank you. That is my conclusion. I also thankful to Ms. Lotaman. Actually, he is present here from the very beginning. So I express my gratitude to her also.
Thank you, sir.
Thank you.
It's my pleasure.
Okay, then we are coming to the last part of our webinar. Now, may I request Mrs. Alaka Deka, Head of the Department Computer Science, to present the vote of thanks. Mrs. Deka,
Yeah.
Mrs. Deka, please go ahead with your vote of thanks.
Okay. Thank you, Mr. Jointer Doctor. A warm and graceful morning to our honorable resource person, Dr. Dipankar Mehdi, Chairperson, our Principal, Dr. Lokbikas Gogoi, and everyone gathered here. Thank you for enlightening us by discussing important science problems such as imaging a black hole and studying black matters in physics through a large hadron collider and how they are connected through computer science, statistics, and computer networks. Now, note that new science problems are data-intensive science problems. This requires us to process lots of data efficiently, for which new algorithms and techniques are constantly needed from a computer science perspective. We also learned that there are measurement errors and sparsity of data, as not everything can be captured fully. For this, it is important to use statistical techniques to have scientific confidence in the results. Finally, computer networks connect everything, since all the data cannot be stored in just one, thus acting like a catalyst to make new scientific discoveries. Now, on behalf of Duliajan College, we would like to extend our sincere gratitude to the resource person, Dr. Dipankar Methi, Program Director in the Computer and Network System Division, National Science Foundation, USA. Dr. Methi, who is currently on leave as Curators, Distinguished Professor in the Department of Computer Science and Electrical Engineering at the University of Missouri, Kansas City under IPA program, has taken the time out for this webinar in spite of his busy schedule. Thank you, Dr. Methi, for your valuable insight. We have been tremendously benefited with the knowledge imparted on us. We would like to thank Dr. Lokbikas Gogoi, Principal, Duliajan College, for guiding us. Thank you, sir, for your valuable inaugural speech and giving us the platform to conduct this webinar smoothly. I would like to extend our wholehearted regards to Dr. Diana Nath, Associate Professor, Department of Commerce, Duliajan College, and Mr. Jayanta Datta, Assistant Professor, Botany Department, Duliajan College, for guiding us throughout this webinar. We would also like to thank Mr. Jayanta Datta for smoothly moderating the webinar. On behalf of the Department of Computer Science, Duliajan College, we would like to extend our sincere thanks to the joint webinar coordinators, Mr. Manoj Kumar Dekar, Assistant Professor, Department of Computer Science, Duliajan College, and Mrs. Munmi Borthakur, Assistant Professor, Department of Computer Science, Duliajan College, for organizing this webinar successfully. This international webinar would not have been possible without them. We also extend our wholehearted gratitude to all the faculty members and students of different colleges for participating and making this webinar a successful one. The Q&A, that is question and answer session, was very interesting and interactive. Thank you, Poppy, for your beautiful question. I, on behalf of the organizing committee, extend our gratitude for all the participants of this session. But last but not the least, I, on behalf of the organization committee, extend our wholehearted gratitude to all those who indirectly or indirectly helped us to organize this webinar successfully. I also thank my elder sister, Mrs. Sakuntala Chaudhary, data scientist from, she's also attending from US, New Jersey, and my younger brother, Mr. Subhankar Methi, and my Horrible, she's Dr. Yashodhara Methi. They're also attending from Guwahati, and I'm in Duliajan, and my elder is in New York. So we are all, and my college is with me. My whole college is with me. So I'm very thankful and happy about it. With this, the international webinar comes to an end. Thank you all once again. Have a good day ahead. Stay safe and take care. Thank you.
Thank you. Okay.
Thank you, Dr.
Bye-bye.
Methi.
Bye.
We
Oh, my
look
elder
forward
sister
to
wants
you.
to say something maybe.
Yeah.
Dr. Datta, elder sister
Yeah, yeah.
might want to say something.
Okay. Go on.
Do you want to say one line?
Yeah, well, definitely. We look forward to
Yeah,
this
yeah.
actually interesting.
Both
And
applications,
your sister
yeah.
also will be shortly organizing another webinar, taking her as the resource
That's
person.
fine.
Okay.
Francis, you have
Am I
to
audible?
মই অসমীয়াতে কওঁ
মই আপোনাৰ
মোৰ নাম-
মানে
Yeah.
হেৰি আমি খুব সোনকালে আৰু এখন ৱেবিনাৰ অৰ্গেনাইজ কৰিম বুলি ভাবিছো। আপুনি কেতিয়া সময় দিব পাৰে সেইটো ওপৰত মানে ডিপেন্ড কৰি পেলাই। So we really look forward to a great family actually, you know, a great family.
We are.
আজি আপুনি ইমান সন্মান কৰি মোৰ ভাইটি দীপঙ্কৰ মেধিক আপোনালোক সকলোৱে ডক্টৰ গগৈ মাতিলে। মোৰ ভনীয়ে বৰ সুন্দৰকে আজি ভাষণটো দিলে। ৰুমজুমৰ ভাষণটো শুনি মনটো খুব ভাল লাগিল। আমাক দেউতাই সদায় সৰুৰ পৰাই কৈছিলে লিবাৰেল আৰ্টছ অংক ফিজিক্স কেমিষ্ট্ৰি বেচিক সায়েন্স জানিবই লাগিব তাৰ লগতে ৰাইটিং আৰু হেৰি কাৰণে মই মানে পিউত পঢ়িলো মুভমেন্ট অফ ইনাৰ্চিয়া ইমান টান পালো ফিজিক্স ভাল নাপাই পেলাই ইকনমিক্স মেথমেটিক্স ষ্টেটিষ্টিক্স পঢ়িলো গতিকে
মইতো
ডাটা
এতিয়াও
সায়েন্স
কেমিষ্ট্ৰি বুজি নাপাওঁ
ডাটা সায়েন্সটো এতিয়াও ইট ইজ আ সায়েন্স এণ্ড আৰ্ট আপুনি ডাটা যদি কৰে প্ৰগ্ৰেমিং কৰিলে ওলাল ৰিজাল্টটো যদি ভালকে ডাটাটো বুজাব নোৱাৰে একো লাভ নাই গতিকে যে সায়েন্স এণ্ড আৰ্ট খুব সুন্দৰকে টেকনিকেল ৰাইটিং লিখিব লাগিব এলগৰিথমবোৰ বুজাব লাগিব লেইমেনক এইটোৱে আচল মানে ইম্পৰ্টেণ্ট গতিকে we all need to be all rounded humanities is very important technical writing how you can communicate your soft skill how you can present your personal branding আৰু তাৰ লগত টেকনিকেল স্কিল ডেফিনেটলি লাগিব ইণ্ডিয়াত টেকনিকেলটো খুব ভালকে শিকায় প্ৰেক্টিকেল স্কিলবোৰ আমি আমেৰিকাত বহুত শিকিলো সেইকাৰণে দেউতাই আমাক সৰুতে কৈছিল সৰুতে ল'ৰা ছোৱালী জাপানত থাকিব লাগে বহুত কথা শিকায় আৰু যেতিয়া কৰ্মজীৱন আমেৰিকাত থাকিব লাগে কষ্ট কৰিব শিকায় আৰু বুঢ়া বয়সত ইণ্ডিয়া বা চাইনাত থাকিব লাগে মানে বুঢ়া বয়স সেইটোৱে ইম্পৰ্টেণ্ট কাৰণ মোৰ হাজবেণ্ড চাইনাত আছিল মাহঁত চাইনালৈ গৈছিলে চীন দেশখন বৰ ভাল পালে সেই সময়ত মই ৩৫ বছৰ ইয়াতে কাম কৰিলো ইন মাৰ্কেটিং সায়েন্স ফৰকাষ্টিং এলগৰিথম এতিয়া বৰ্তমান কোভিড ৰিলেটেড হেৰিত টাস্ক ফ'ৰ্চত আছো ইণ্টাৰনেশ্যনেল টাস্ক ফ'ৰ্চ ইণ্ডিয়াৰ কিবা ডাটা থাকিলে ময়ো এনালাইজ চাব পাৰিম আৰু তাৰ লগতে মই ইউনিভাৰ্চিটিত জইন কৰিলো আফটাৰ স্পেণ্ডিং 45 years ইন একাডেমিয়া এতিয়া পাৰ্ট টাইম প্ৰফেচাৰ নিজৰ ডাটা সায়েন্স হেৰি শিকাই আছো গতিকে ডিবুৱে যিবিলাক ক'লে খুব ভাল কথাই কৈছে অপেন চ'ৰ্চবোৰ কিন্তু যদি ল'ৰা ছোৱালী সদায় ভাল কোম্পানী গুগলত সোমাব খুজিব পাৰে AT&T ইণ্ডিয়াত সোমাব খুজিব তেতিয়াহ'লে অন্য কিছুমান প্ৰপাৰ্টিৰ ছফ্টৱেৰ শিকিব লাগিব মেথমেটিকা SAS so that the algorithms are within the company নহ'লে অপেন চ'ৰ্চ হ'লে মানে ভীষণ হেৰি হয় লিগেল ইছ্যু হৈ যায় ইউনিভাৰ্চিটিৰ কাৰণে খুব ভাল শিকিবলৈ কিন্তু গোটেইবোৰ লাগিবই এই পাইথনটো ঠিক ইংৰাজীত ইউজ কৰাৰ দৰে পাইথন আৰু SAS ধুনীয়াকে লাইনবোৰ লিখি দিয়া চিকুৱেন্সটো এটা গল্প কৈ দিয়াৰ দৰে ডাটাটো ৰিড কৰিলে কেনেকে হেৰি কৰিলে গতিকে ইট হেল্পছ উইথ দ্য চায়েন্স এণ্ড আৰ্ট আৰু মানে ইট টেলছ দ্য ষ্টৰি চ' ইউ হেভ ইউৰ চিকুৱেন্স চ' পাইথন ইজ ডেফিনেটলি ভেৰি গুড এইখিনিকে কোৱা আপোনালোকৰ ভাগৰ লাগিছে আমাৰ ইয়াত 2টা বাজিব হ'ল ভণ্টি মৰমতে আজি দেউতা মা নাই একগোট হলো 4জন আপোনালোকৰ অনুৰোধত জয়ন্ত দত্ত বিকাশ গগৈ আৰু মনোজ দেখাই নাপালো ক'ত গ'ল মনোজৰ মুখখনেই দেখা পোৱা নাই
সেই ভিডিঅ'টো অফ কৰি থৈছে
আৰু মন্নি বৰঠাকুৰ নেকি মন্নি নাম শুনি আৰু গোটেইখিনি অডিয়েন্সকে বহুত ধন্যবাদ জনালো শুধু আমেৰিকাৰ পৰা কভিডৰ উৎপাতত কেতিয়া লগ পাওঁ গোটেই পৃথিৱী সলনি হৈ গ'ল 1819ত স্পেনিছ ফ্লু হোৱাৰ পাছত 1919ত তাৰপিছত 1948ত আফটাৰ ৱৰ্ল্ড ৱাৰ II এতিয়া কভিডৰ পিছত এটা নিউ ৱৰ্ল্ড অৰ্ডাৰ গতিকে চবেই ভালে কুশলে থাকিব with thoughts of safety peace and health নমস্কাৰ থলো
ধন্যবাদ মেডাম আমি মই মেমৰ যে ফেমিলিৰ আৰু মেম্বাৰ আছিলে মই নাজানিলো মই সকলোকে মোৰ ফালৰ পৰা পুনৰবাৰ মই ধন্যবাদ জনাইছো
দেখিছে যশোধাৰা মেধি মোৰ সৰু বৌ দাদা ইঞ্জিনিয়াৰ তেওঁ শুভংকৰ মেধি এয়া ডাঙৰ দাদা দীপংকৰ মেধি দাদা ইঞ্জিনিয়াৰ
মই কথা জনাইছো আপোনালোকৰ হোল ফেমিলি লৈ
দুটালাই ক'বও পাৰে তেওঁ কলেজৰ
আপোনালোকৰ আশীৰ্বাদতে আজি এনেকে মানে ভাৰ্চুৱেলি